So we've already talked about coordinate systems that we can apply to the sky. We've talked about constellations, how the stars move in the sky and how they change with time and behave. But what we haven't discussed is planets. What do they look like in the sky? How can we spot them? And why do they behave differently to the stars? So a quick recap. What are constellations? Remember, a constellation is simply a group of stars, but may have more than just a star identified within it. A constellation can contain a galaxy or a nebula, a supernova, or a planet. Now the thing with planets is they move differently to the stars. So do asteroids, comets, and of course meteors, which can appear in the sky at any number of positions. They will all be defined as either passing through or briefly being in a specific constellation. So a planet on its journey across the sky will move through a number of constellations rather than being a member of any one group. And remember, constellations visibly change over many thousands of years due to things like precession. Planets, on the other hand, change much more quickly and for other reasons. So first of all, why do we call them planets? Why don't we call them little rocky stars or something? Well, planet comes from the ancient Greek, the word planetai, which means wanderer. So all the planets in the solar system actually orbit in nearly the same plane and move around in their orbit, and as such move in the sky relative to the stars, hence the name wanderer. The plane that the planets are on is very nearly on the ecliptic, and remember our definition of the ecliptic. It's the path of the sun across the sky over the year. So if we look at the orbits of the planets, here's Earth. We're using Earth as a reference point for the plane of all the other planets. So Earth is set at 0 by us, and that means we can look at how much inclined the other planets are. The orbit of Mercury, 7 degrees, quite an extreme inclination. Venus at 3, Earth at 0 of course. Mars, almost 2 degrees, Jupiter 1, Saturn 2. So most of these planets are falling between about 1 and 3 degree inclinations. Uranus, very close inclination of orbit to the Earth. Neptune, not too bad. And Pluto, one of the controversial reasons for its planet status is its orbit, and its orbit, as you can see, is about 17 degrees. That's at least 10 degrees more than the inclination of the most extremely inclined inner planet. So that was one of the reasons why people were a little unhappy with Pluto's planet status. And what do we mean by those inclinations? Well, what we mean is every planet in the solar system is not just on one flat plane like a record. Some of them are a little higher, some of them are a little lower, and if we set Earth at 0, all of those previous values tell you how much above the plane of the solar system these things are. So here's Pluto with its really pronounced 17-degree tilt compared to the other planets. So Pluto's coming up out of the plane of the solar system and down below it. Pluto actually intersects the orbit of Neptune. Sometimes Neptune's the furthest planet from the Sun, sometimes Pluto, depending at what point these two planets are in their orbit. All of the inner planets fit into this little ring here. So if we zoom in, there's all our inner planets, and you can see how pronounced Mercury and Mars's tilt is to the other inner planets. So that's all well and good. That's how the orbital planes work. This is how the planets move around their orbit, and their path across the sky will be affected by that. So what do we see in the sky? Well, we can't really see these planets during the day, of course, because the sun is so bright and masking them out. So if we look for a planet, we have to look near that ecliptic plane. Here the sun is down below the horizon. So here's the horizon with little trees on it, and the sun has just set. Well, it's just rising. Here's sunset, here's sunrise. So the sun is just rising here. So around sunrise, if you want to go and see Mercury, that's the best time to go see it. And indeed, Venus is visible a lot more. Mercury is the more difficult of the two to see. And there's why. That its orbit's very small, so it comes up above the horizon and disappears below the horizon quite quickly. So all the planets are orbiting in nearly the same plane. Venus and Mercury are never far from the Sun, so you do have to look for them during sunrise, or conversely during sunset in this diagram. Mercury can actually become an extremely bright object. Venus is bright and tends to be present in the evening and morning sky much more than Mercury. You do need a clear horizon over an ocean or a lake, perhaps, instead of in an urban environment or anywhere where there's a lot of trees, to see something like Mercury, because it never really gets to high elevations. But here's the ecliptic, and here's the path of Venus and the path of Mercury. So you can see they're very close to that ecliptic plane, because their inclinations, a maximum of about 7 degrees for Mercury, are not too far off. So if you want to see a planet, you have to look along the ecliptic. And when you're looking at this, the ancient people noticed this and said, well, what's our solar system like? Well, this is evidence that the whole system orbits in a plane, because all of the planets are very close to the ecliptic. So how does this change how planets move in the sky? Well, planets don't move across the sky in the same way that stars do. Planetary motion is dependent on where the planet is in its orbit. It depends on the progress of the planet in its orbit, the planet in question, be it Venus, Mercury, Mars, Jupiter, whatever, and Earth in its orbit. So over time, a planet will be seen to travel through many different constellations. And these planets, when people did not know that these were rocky or gaseous bodies orbiting in our solar system, was a serious form of confusion. All of the stars were going one way, and then suddenly these planets would start doing different things. And I'll show you what we mean by this. Well, here you can see this is Jupiter in the sky and Saturn in the sky. Jupiter is this bigger blob of the two and Saturn is the smaller. And you can see what's happening. Here's the stars, relatively stationary in the sky, and these two bright things that we now know are planets, of course, come across the sky and then turn around and go back in the opposite direction. Now, for an ancient scientist trying to figure out the nature of the universe, it's a little bit confusing as to why that would happen. You figured out the Earth rotates, you figured out the Earth is moving, and then suddenly these objects start doing this. Mars is even worse. That's the moon skipping through during this simulation there that you can see, showing you the passage of time. So this is months worth of motion. Not just a few days or a few hours, but months worth of motion. So Mars does these sort of squiggly zigzag patterns in the sky, which caused even more confusion for people. These planets were then not all just moving in the same fashion, but were actually moving differently one to another. And we actually refer to this as retrograde motion, when an object is moving across the sky, turns around, and then goes back in the opposite direction. So here's Mars coming in and leaving this loop in the sky if you were to draw a line behind it. So if you were to go out on multiple different nights and observe the path of Mars, you would actually see this over a period of months. Mars would do this zigzag. And this is a series of images all superimposed onto the same background to show you how Mars is moving. So Mars is moving through Libra, Scorpius, and then finally through Ophiuchus. But it stops while it's in Scorpio and goes backwards and forth, back and forth a little bit, and then continues its journey in this direction towards Ophiuchus. Saturn, on the other hand, is relatively well behaved, but still not perfectly behaved, and he's kind of just jiggling back and forth between Ophiuchus and Scorpius. And this is one of those things, if you ever look at an astrology report and then compare it to real astronomy software and the positions of things in the sky, where astrologers will often tell you that Mars is currently whizzing through Libra, and you're like, no, it's not actually, it's in Cassiopeia. But anyway, they often get these kinds of things wrong. But here's the path that Mars will take compared to, say, Saturn. So on the whole, planets usually are behaving themselves and moving relative to the stars eastward, just like the Sun would. Occasionally then, they turn around and move west for a while relative to the stars and then go east again. And you do have to look out multiple nights. You can't just go out on one night and see this zigzag pattern. You would have to go out for a month or more and then chart the position of the planet in the sky to see this change. And this was a lot easier for ancient peoples who did not have a lot of light pollution or cities getting in their way. They were much more aware of the stars and used them much more as calendars and were much more culturally important than they are today. So they often notice these changes, whereas modern people do not. But over multiple nights, you can see this change. On a single night, you'll see it simply rise in the east and set in the west. So, what about retrograde motion? Well, when people were trying to figure out what the universe was like, not even realizing quite what the nature of the solar system was, they were trying to come up with a model of the solar system. What did the solar system look like if you saw it from above? And models really showed everything revolving around in a nice orderly fashion. And then suddenly these planets did this. So explaining why a planet would go backwards in the sky was a serious problem to an ancient astronomer, especially when they didn't know the difference between the background stars in their nature and the planets themselves, and thought they were made of the same stuff. In the old model of the solar system, and of course the whole universe, the Earth was at the center, and this was people's starting point for their models. So it was believed that all objects revolved around the Earth. Any system we're talking about where everything goes around the Earth is referred to as the geocentric system, a geocentric solar system. Earth is at the center. So, in order to account for these weird motions of the planets, they had to make elaborate changes to their models. And, of course, people decided, well, maybe the model is wrong. Maybe the way we're thinking about our solar system is incorrect, and there's another way that it's actually structured. So, multiple models popped up. There was the traditional Earth-centered geocentric model. The Earth stays unmoving at the center of the solar system, and everything else moves around the Earth. This makes logical sense if we look at the sky, of course, and see the sky moving. The second was the sun-centered model, or heliocentric system as it was referred to. The sun is at the center of the solar system, and everything else moves, including us. So the Earth was revolving, and it was moving around the sun in its progress over the year. There was other models, of course. There were other models, and there was a quite well advanced model, which was Tycho Brahe's model, which was a geo-heliocentric mix. It took both of these models and kind of fused them together. And that left the Earth unmoving at the center, but the sun goes around the Earth, and then everything else moves around the sun. So this is kind of a mix of a geo and heliocentric model. And these were the three competing models for quite a while. So the prevailing view for a long time was Ptolemy's model, and Ptolemy was around 90 to 168 AD, and the Ptolemaic system really dictated how astronomy was done. He was sort of a polymath, a sort of Renaissance man essentially, long before the Renaissance. He was a Greek musician, an astrologer, an astronomer, and he worked extensively on predicting patterns and cycles of things in the sky, and his system became the standard one of which everybody judged the motion of the heavens. So in his model, Earth was at the center, the sun orbited the Earth, and the moon orbited the Earth, and so did everything else. Now, if you want to account for the retrograde motion, you can add what are called epicycles. And bear in mind, we now know this model is wrong, but this was how they accounted for retrograde motion. Here's the Earth at the center, and here's the orbit of Mercury, Venus, Mars, Jupiter, and Saturn. Look where the Sun is. We know, in terms of the order of the planets, that we have Mercury, Venus, then Earth. In the Ptolemaic or geocentric system, the Sun is where the Earth should be. So there was some logic to how this was figured out. So some people laugh at these models today, but that's kind of unfair. Based on rudimentary observations, this actually isn't too bad. But here's the Sun in place of the Earth. Now, how do we account for this retrograde motion? Well, these little rings show the planets orbiting inside their orbits. They're not orbiting any particular mass. Remember, these people are actually working without knowledge of Newtonian physics, without the physics that we know today, so don't realize quite how orbits work in terms of energy and in terms of forces. So here's here's Mercury's orbit, and here's Mercury going in another little ring, and Venus going in another little ring. And apart from the Sun, everything has its own little circle that it moves in while it's moving around in its main orbit. And that's the effect you would have on the sky. The epicycles successfully explained why the planets would go backwards against the pattern of stars. So here's the stars in the background, and here's the planet tracing out its S. So if this is Mars, this would be Mars tracing out that weird zigzag as it moves forward, as it progresses in this little circle versus its bigger orbit. It appears to go backwards relative to the Earth. So that explained retrograde motion. Mercury and Venus were fixed to the Earth-Sun line, and that meant the effects were less pronounced than some of the other planets. There was then the Copernican model, the heliocentric model that came along. Copernicus often gets credit with having originated this model. He really didn't so much as champion it and publish it in a very controversial paper at the time. But the idea of a heliocentric system goes back much further, and Aristarchus actually proposed this idea back in 300 BC, that maybe the Sun was the center of the solar system and not the Earth. And this is really the system that we know today is correct. So the Sun is here at the center of the solar system, and then we have Mercury, Venus, Earth, Mars, asteroid belt, Jupiter, Saturn, all the way out here to Uranus and Neptune, with the Moon orbiting the Earth to account for the motion of the Moon. So the Moon here is not a planet in its own right, it does orbit the Earth. And here's one of Copernicus's original drawings from his treatise on the heliocentric model that caused so much consternation. So here's our system. Here's all of the terrestrial planets down here in this ring, Mars, Jupiter, Saturn, all in orbits moving outwards from the Sun, and all just going around the Sun. So Copernicus, as I said, did not come up with this idea wholesale, but was actually a champion of this idea, published his paper De Revolutionibus Orbium Celestium, and stated the heliocentric theory. But different to everybody who'd come before him, Copernicus provided proof of the heliocentric system, and that was really what made this a different paper. So he published this paper, and it turned out to be a little bit controversial in a number of areas, and was quickly banned. So here's the two differences. Here's the Ptolemaic system. Here's the Earth. Here's the Sun, one astronomical unit, the Sun going around the Earth, and here's the epicycle of Mars, which means Mars has to come all the way in to the inner solar system and go back out on its circle. If we look at the Copernican system, it's actually a lot simpler, And scientifically, the simplest explanation is nearly always the correct one. Not always, but mostly. So here's the Sun, here's the Earth at its 1 astronomical unit, and then you have Mars. It's at half an AU here. So this is half an AU from Earth to Mars. So here's Mars's orbit, here's Earth's orbit. A little neater, a little more elegant. And then, of course, no discussion of these models is complete without talking about Tycho Brahe's hybrid model. And we'll talk about Tycho in a bit more detail later as a character in his own right, actually in the next slide. So in Tycho's model, here's the Earth at the center. This is from his actual paper. Here it says Hypothesis Tychonica. This is his own handwriting, his own diagram. Here are the stars in a sphere, as it says here, sphere stellarium. And then here's the planets going round in their orbits. The moon, the sun, and the stars go around the Earth, but then all the planets go around the sun. And this did account for the same effects. Tycho was an interesting character in himself, and Tycho was beloved of the geocentric model of the solar system and didn't want to change it, so came up with his own version there. He was a teacher and colleague of the famous Johann Kepler, who came up with Kepler's laws. We'll talk more about their relationship later, but Tycho himself was a bit of an interesting character and had an artificial nose made out of gold, having lost a chunk of his nose in a duel over a mathematical equation. He was sort of a rock star scientist of his day and actually had a pet moose and a dwarf that used to tell jokes at his parties. He eventually died spectacularly at a banquet. Some say from overeating, some say from a ruptured bladder. There is a theory that gets a little bit Scooby-Doo that discusses that Kepler may have poisoned him. I'm not so sure on this, knowing a little bit about the character of Kepler, but it's still an interesting idea. So, in terms of the heliocentric model, people would say, well, the heliocentric model's all well and good, but it can't possibly explain retrograde motion. But it does. So retrograde motion is actually explained in the heliocentric system by the lapping of planets. Venus and Mercury are inside the orbit of Earth and travel faster than the Earth because of their smaller orbit. They don't have as far to go. Mars and the other objects are further out, and the Earth overtakes them in its orbit as it moves around the Sun. This is the problem that Kepler will solve much later, and this shows the slow progress of astronomy over decades and centuries as people reason things out. So, in the heliocentric system, here we have the Sun, here we have Earth, and here we have Mars, and here we have the background stars. So we look out from the Earth and we see the stars here, and we see the planet projected against the stars. So if we stand on the Earth and view Mars, we're standing here. Here's our line of sight. We see this planet Mars against the background of stars here at point 1. Now as time moves on, Earth moves in its orbit, but Mars does not move nearly as far in its orbit as Earth does, as Earth is going faster than Mars. This means we're then looking back on Mars. So here we're neck and neck. Over here, Earth is winning the race and ahead, and Mars is behind it. So as we look back on Mars, it appears that Mars has gone backwards. In actual fact, Mars is moving forward in its orbit in exactly the same sense that Earth is. It's just not going as far. So as we look back, we see Mars at position 2 against the stars. So to us from the Earth, it looks like Mars went backwards, when in reality, Mars is moving forwards. And here's just an animation of the same effect. Here's the planet moving in its orbit, and here's Mars moving in its orbit. And as you can see, this line of sight traced out by the yellow is showing you where the image of the planet will appear to be. So here's the sky view, and here's the orbital view. And you can see that as the planet passes here, as it starts to lap it, the planet appears to go backwards in the sky, even though both are moving forwards in their orbit. I apologize for the state of some of these GIFs. They're a little older, but they are very successful in showing the effect we're talking about. So there's the Earth moving, there's Mars moving, so here's Earth, a terrible cartoon sun, and Mars, but it still shows the effect. Earth moves around and projects this zigzag pattern of Mars against the stars. So for a long time there were competing models. And how do you know which model is correct? Which one do you prefer? And as I said before, the simplest is usually the most correct. The sun-centered model is the simplest. It's neat. It has a nice, simple explanation of retrograde motion without need for weird epicycles, of which there's no real reason for these planets to go in the extra little circles in their orbits. So the planet paths are simplest in the heliocentric system. However, people didn't like it because they said, well, if the Earth is moving, why do we not feel this great wind? Why does the Earth not feel an enormous resistance to its motion? They didn't understand that space is really a vacuum, almost a vacuum, few particles per cubic meter. They didn't understand this particular effect, and that to them was a very difficult thing to take in. What's the Earth moving through? Why does the atmosphere not continue? So people needed to come up with reasons which model was correct. And what we really had to do, and what you should do in every science, is take your model, take the ideas that you have developed and mathematically shown, and compare them to actual real observations. So observations were really needed to test the heliocentric model. And what really confirmed this and made it certain that the heliocentric model was right was the telescope. So technology really assisted here. So proof of heliocentrism was really needed. And that proof really came in the point of observing Venus, the form of observing this planet. So if Venus is a bright planet, it's easy to see. It's also an inner planet. It's inside the orbit of the Earth. That means that Venus should show phases very similar to that of the moon. Sometimes you'll see half moon or a full moon or a very sliver crescent moon. And we should see the same effect with Venus. So if the heliocentric model is true, we should see those effects with Venus. Venus orbits the sun, its phase should change. And this is where Galileo steps into the argument. Now, Galileo did not invent the telescope, as some sources will tell you. Many people were looking to invent such a device, and Galileo definitely read about the discoveries of other people and the optical devices that they were building. But he did build his own telescope. We cannot take that away from him. And his telescope was quite advanced compared to those of the day, even though by today's standards his optics were extremely poor. Now, initially, Galileo, being an educated man and a scientist, didn't turn his telescope always to the stars. Galileo had a number of children and bills to pay, and Galileo used to use his telescope for observing the flags of ships coming into port. Why? Well, some of these flags would actually tell you what the ship was bearing. Did it have oil? Did it have whale oil and bone? Did it have gold? Did it have spice? What was on board this ship as it came into port? Galileo could use his telescope to see what flags the ship was carrying and then run down to the stock exchange before everyone else and put his money in the right places. So Galileo could use his telescope for a number of different reasons. But what we do know is Galileo did funnel a lot of his own personal time, energy and funds into developing ever better telescopes. And here's an example of one of his telescopes, a wooden tube with a lens at one end and a lens at the other. We'll discuss more about the workings of telescopes later on. And then quite often bound in leather. And Galileo did a lot of astronomical observations. Here are his observations of the moon. He showed that he could see detail on the other side of the moon. This is called the terminator. We'll discuss that with the moon. This is the terminator, the delineation between light and dark on the moon. And he saw detail on the other side of the terminator, showing this it wasn't completely dark and that part of the moon was not disappearing. So he observed the moon phases. He looked at the craters and made very good drawings of the moon. He looked at Saturn, but his telescope was not powerful enough to see that this planet had true rings. So what you ended up with was a planet which had sort of cup handles sticking out the side, which as an object became very, very confusing to astronomers until they managed to get a better telescope. And then of course you have objects like Jupiter and Mars, which he showed to be disks and not just point sources in the sky like a star. But one of his main observations was the phases of Venus. Here's Venus in full, half, and then as it waxes or wanes, you'll see crescent phases of Venus. So you can see the phases of Venus versus the phases of the moon. This is due to the fact that Venus is moving in its orbit and being illuminated from different angles by the sun. This creates this effect of phases. And that means that the heliocentric system could explain the phases. This was proof of the heliocentrism. So if you go outside on any particular night and look at Venus, you won't see a chunk out of it. It's a very bright planet due to all of the carbon dioxide in its atmosphere. What you'll see will be this. If you put a telescope on this, about a 200 times magnification through a 6-inch telescope here, you will actually see that Venus here is a crescent. It has a phase. Incidentally, if you go out into a dark sky site at any particular point and look into the sky, you will often see planets in the sky like this. Some people have seen planets their entire lives and not known they were planets. Indeed, I have talked to police officers who spent an entire night chasing Venus across the moors of England. So here's why this happens. Here's the Earth and here's Venus going round on its inner orbit. And this is why these phases gave us proof of heliocentrism. When Venus is here, the sun is illuminating its full face. As it moves around, it goes into what we call the gibbous phase, where a little tiny piece is missing as the sun is illuminating it from an angle. When Venus is over here, we can see exactly half of it, then a crescent. When it's in the new phase, confusingly, this is when Venus is completely black and is not visible because the sun is here and illuminating it from the wrong side. This is not eclipsing the sun, it's just not illuminating it relative to the Earth. Then Venus comes back. As it moves in its orbit, it starts to illuminate again and goes through the same series of phases back to full. So this was what Galileo saw, and this was part of his controversy. He didn't come up with the heliocentric system. He simply supported Copernicus's ideas. Copernicus did the proof, Galileo made the observations and published them. And here is a geocentric system. If we look at the geocentric system with the epicycles in place, you would not get a full family of phases. You wouldn't see those crescents and waning gibbous and waxing gibbous phases so much. What you would get instead of a lot of phases is really two distinct ones. You would have it's new, or you'd have a half or full. New, full, half. So heliocentrism showed that you should see all of these phases, and that's what Galileo saw. He observed on multiple nights and he observed all the phases of Venus and proved that the heliocentric system that Copernicus had championed was correct. So he would have seen something like this, but not in as great a detail. And here we actually have the percentage of the planet that's illuminated written below. Galileo published this work in his paper Sidereus Nuncius, March 13, 1610, actually translates to Sidereal Message. And this represents the first published paper that actually used telescopic observations. So this was quite a landmark paper in its own right. And this is where Galileo's fight with the Church, or more specifically, one cardinal, namely Bellarmine, comes into effect. So Cardinal Bellarmine was a highly respected man, but had previously been involved with the execution of Giordano Bruno, where he was burned at the stake for suggesting that stars were other suns and that there were planets moving about them the same as the sun. And it was Cardinal Bellarmine that noticed Galileo's work. Bellarmine himself was actually a very active cardinal and was actually canonized in 1930 and did a lot of good works, but he did not like Galileo and his work. That's not to say that the Church was necessarily against Galileo. His friend Paolo Sarpi was a member of the Church and supported Galileo's work, and a number of very high-level cardinals were very interested in the kind of work that Galileo was doing. So there is a myth that has popped up of Galileo standing defiant in front of the entire Church, fighting against them. And this is a bit of a myth. Galileo himself had the support of many influential people in the Church, which is probably why he was not executed when he did not recant his discoveries, and instead was just forced to be essentially pulled into an inquisition and told to sign that his discoveries were wrong. Galileo himself actually, in later years, even questioned whether his heliocentrism was even right, a point that's often lost by historians. But we do know Galileo was indeed right. These fights did exist, but historically they were a lot more complicated than people give them credit. But there was still a problem. There was the last vestiges of geocentrism holding on. The phases of Venus showed that the Copernican model could be right, but was it right? Tycho Brahe's heliocentric geocentric mix model still worked. It still predicts the phases of Venus in the same way that heliocentric system would. And that was a bit of a problem. That meant we couldn't now throw away a geocentric system and then go for the heliocentric system, even though we now know this was the correct one. So more proof was needed of the heliocentric system. And part of the support for Tycho Brahe's model was that we didn't need something called stellar parallax. Now, in the Copernican model, we should see this effect called parallax, but not in Tycho Brahe's model, which meant people started to favour the geocentric model of Tycho Brahe, even with its enhanced complexity. Now, stellar parallax is actually a movement in the position of the stars due to the motion of the Earth in its orbit. And the reason they could not see it in the 1600s is because you really need a telescope. You need accurate observations and instrumentation in order to see the parallax of the stars. So before we continue here, let's talk a little bit about what parallax actually is and define it a little. So in the sun-centered model, this means the Earth is moving great distances around the sun. As the Earth moves around the Sun, you should view the stars from a slightly different point at every point in your orbit. Consequently, we should see the stars move a little bit in the sky due to this motion of the Earth, and that's what we mean by parallax. the apparent shift of a star's position due to the Earth's motion around the Sun. You can see an effect of parallax if you're driving in a car down the street. If you're moving at 70 miles per hour, for instance, all of the street signs and the scenery and the buildings are zooming by you at 70 miles per hour. If you watch the moon, you are not really moving relative to the moon. The moon appears to be moving right along with you and stays stationary next to your vehicle for your entire journey. So in order to observe the parallax of the moon, you would have to move quite a long distance. Now remember, the moon is a very big object, so even a slight shift in your position will not really move it in the sky that much. So here, if you are in this car played by the Ghostbusters Ecto-1 here, and viewing the moon from point 1, we will see the moon against the background stars in this position. Even moving a very long distance, the diameter of the moon is very, very large. So you won't actually see much of a change in position, even though your perspective has changed and you are observing the moon from a different angle relative to the diameter of the moon, you won't see much shift. Now, a star is much, much further away. And part of the problem here, if we're looking at a specific star, is a nearby star will shift position, but very far away stars won't shift position quite as much. So you need a telescope to see this. Stars are very, very far away, and this parallax angle is a difficult thing to detect. But it is there. So here's the Earth in January. We're observing this star, and here's the background stars, which are much, much more distant, and here's a star in the foreground. That means in January, we will see the star in this position versus these background stars. The Earth then moves around in its orbit to the other side of the Sun. Remember, this is a 1 astronomical unit radius. We'll move all the way around to the other side of the Sun, still observing this star. This star will appear in July to be over here in this position. That's what we mean by parallax. And what that will mean is as the Earth is moving, and this is exaggerated, remember, this has been exaggerated a bit so you can really see what the effect would be. The stars in the sky would appear to do this. So we're moving here left and right as we circle around the Sun, and this is the kind of effect you'd be looking at for the stars. Now you don't see that when you go out and look at the stars with your naked eye. In order to detect this, you need a telescope and a way of measuring the position of the stars inside the telescope. So the stars were so far away that stellar parallax was too small to see with the naked eye. Telescopes were in limited use at the time, and Galileo's telescope really was not accurate enough and not of optical quality to actually discern this effect at all. So this left a question mark hanging over the heliocentric system a bit. Now, eventually, of course, people did decide the heliocentric system did work out better, and the planetary motions of Tycho Brahe were a little bit complicated. But even the heliocentric system did not perfectly predict planetary motion. The heliocentric system still assumed that orbits were perfect circles, and this is where we'll be going next. Orbits are really elliptical, which means if you use a perfect circle and try to mathematically predict the position of a planet in the sky, it won't be quite right. It'll be close, but they'll still be off because an orbit is not perfectly circular. And this is what Kepler endeavored to fix later on in this story. So the planets are actually in these elliptical orbits. There is further confirmation of the motion of the Earth and the Earth's rotation, looking at things like the Coriolis effect, a deflection that occurs with rotating storms like hurricanes. And there's also something like the aberration of starlight as Earth actually orbits the sun. So the starlight is actually angled a little bit, like you're driving through snow or rain, where the snow and rain appears to come at your vehicle even though it's falling perfectly vertically. So there's a diagram of, or an image even, of Foucault's pendulum. This is a pendulum you can hang from a ceiling, and then often people put dominoes around here, and what can happen is as the Earth rotates, the pendulum will shift and will knock over these dominoes in succession. It actually makes quite an effective clock for showing the rotation of the Earth. Galileo actually did a lot of other astronomical work too. Let's talk a little bit about that before we move on. Galileo greatly improved telescope optics. He didn't just have one telescope. He built his first crude telescope based on ideas coming out of the Netherlands and possibly even Britain, based on papers that were sent to him, but then improved it. He built successively better telescopes. He also did observations of the moon, showing the shadows that were cast by mountains on the moon. He looked at the sun, something I must say, as usual, my caveat, please don't look at the sun through a telescope. But Galileo did, and saw sunspots on its surface, and may have been one of the first people to ever report these spots on its surface. Again, Galileo didn't actually invent the telescope. Even as early as the late 1590s, London newspapers were actually advertising a telescope that could see features on the moon. So people were indeed turning telescopes all over the world towards the sky and gazing at these objects. Galileo's achievement was he was the first man to make scientific determinations and publish them from his telescopic work. Galileo also showed that there were systems that were not really circling the Earth. He looked at Jupiter, and these are drawings from Galileo's own notebook. Here is Jupiter, and he actually came up with what we call the Galilean moons, and was the first to observe them. These are Europa, Ganymede, Callisto, and Io. And here are those moons, the 4 inner moons of Jupiter. I believe there's around 60 plus moons now identified around Jupiter. But he could see these 4 and noted their positions on multiple nights and how they changed. He saw these bright dots, and you can see this with basic binoculars and telescopes. Any sort of binoculars will often show you these moons around Jupiter. So here's the real telescopic view, better than Galileo would have had, for you can actually see detail and see the cloud belts here on Jupiter. And here's what was really going on. If you go out over multiple nights and observe this system, you'll see these little dots of light changing position. These are the moons revolving around Jupiter, and these were his notes. Here's Jupiter's disk, and here's 2 dots. You went out another night, saw 2 dots here, 1 here, 3 on one side, 2, 1, 2 here. Sometimes these moons are either behind or in front of Jupiter where he couldn't see them, hence them being missing. But on a good night, he could see all 4, Io, Europa, Ganymede, and Callisto, all here. And we'll talk about these moons in a bit of detail later. So Galileo was definitely an influential scientist and did a lot of extremely good work. We'll continue this discussion and look into Kepler's laws and the motion of planets in the sky a little more.